Welcome back. Today we're going to talk about principal components analysis. This is very commonly used in machine learning applications because it's a way of taking high-dimensional data and effectively decreasing the dimensionality of that data. But it has applications beyond that. Anytime you're doing classification or analysis of data, it's helpful. It may be helpful. There are some weaknesses to PCA that we may talk about, but here's an example of data. You have to use your imagination since you're looking at a two-dimensional surface, but this data exists in 3 dimensions. Now we would like to approximate this data in just 2 dimensions, and so you can see this green grid there where we would be projecting that data back down onto this 2-dimensional surface. It's an example of where PCA might be used. Now PCA is often discussed in statistics classes as a way of, as a transformation based on the second order statistics of the data. And one way to get some intuitive sense for PCA is to essentially look at what it would do to data like this. This data could, in this particular case, be modeled by perhaps a Gaussian, and it would have a variance in those 2 different directions. And so PCA would find the direction with the largest variance and project the data onto that dimension. Or if there were very high dimensional data, you might choose multiple dimensions as subspace and project the data onto that. So we're going to be looking at PCA as finding a subspace that most closely approximates the data we've got. This is very similar to the total least squares that we looked at previously. So first I'll introduce a few numbers here. We have N is our number of data samples, and it tends to be large. D is the dimensionality of our samples. In the case off to the left, that would be D equals 3. And K is the dimensionality of our subspace. And in this case, K would be equal to 2. Now, strictly speaking, it's not a subspace as we've been talking about. It's actually an affine subspace. So I'll just say affine space. And an affine space is a subspace with an offset. So we know a subspace has to be a space in and of itself, which means it has to include the 0 vector. An affine space does not have to include the 0 vector. So it would be a subspace with some vector offset added to it. Okay, so our goal is to find 2 things. U, that's the dimensionality of our original samples, and a orthomatrix Q. Actually, let me express this explicitly. A matrix Q with orthonormal columns. So Q is D by K. All right, and such that xn approximately equals mu, and mu is a vector, so I'm going to redraw this to be darker, plus q theta sub n for all n equals 1 to capital N, or total number of samples. And that, you know, for some theta. That is k-dimensional. Okay, so we're given the data samples, and we can cast this as an optimization problem in which we're trying to minimize over mu, q, and theta the sum of the squared approximation error and of course subject to q transpose q is equal to I. So q isn't square, so we don't have it the other way around, but we have that columns are at least orthonormal. So it's a lot of things to optimize for at once. Let's knock one of them out of the way to start with. So we'll start by fixing mu and defining x tilde is equal to of n is equal to x of n minus mu. Okay, so once we have this, then the problem gets a little bit easier. In fact, let's do a couple more things at once. Now we're just minimizing the difference between x tilde of n and q theta of n. And since we're looking at this sum of the total squares, we can actually rewrite this as some color, minimizing q r d by k, and capital theta, that's k by n, capital X minus q, capital theta, Frobenius norm, with the same restriction on q as before. So the first expression we looked at there in blue was finding the difference between x tilde and q times theta n for each column, and then adding up all of them, the sum of all the, adding the squares, all of them. And the Frobenius norm is doing the same thing. So this is kind of nice because this is related to what we've discussed with our total least squares approximation, or from our earlier lectures. And that is that our best subspace approximation occurs when we approximate x tilde with the first k columns of the SVD of u times, of course, its singular value. And so this problem is solved by using the SVD, find a low rank approximation of x tilde, and we do that by saying if x tilde has an SVD of u sigma v, then we just say q hat is equal to uk, theta hat, our approximation, is equal to uk transpose x tilde. So here we have that uk is equal to u1, u2, the first k columns of u. Okay, so if we look at, let me just copy this down. First we'll put we have that q hat is equal to uk, and theta hat is equal to uk transpose x tilde. So what does this mean? Well, x tilde is equal to u sigma v transpose. So this term right here, having just the first k columns, is going to give us a k by k identity matrix, and then zeros, because those first k columns are orthogonal to the remaining columns of u. That remains the same, and that remains the same. And so this is going to pick off the first k singular values, and the others are going to be 0. Which will then kicks off the first k rows of V transpose. Okay, so this effectively is saying we are now, by looking at Q hat times theta, so Q hat capital theta is our approximation of x tilde using the first k singular values setting the others to 0. And we've already discussed how this is a good way to find our least squares, best least squares approximation to a matrix. So now that we've got this, let's go back and see how we can find our optimal mu. Because once we have our mu, and therefore our x tilde, we can come up with our approximation. So the one thing we left out was mu. So we had theta sub n is equal to Q transpose xn minus mu. So we can get there from this highlighted term right there, and that Q transpose times Q is equal to the identity matrix. And so subtracting mu from both sides and then multiplying by Q transpose will give us our theta. So it's exactly where we're at now. And we can plug this in to our objective function we were trying to optimize before. And we have xn minus mu minus q theta n is equal to xn minus mu minus q transpose xn minus mu, which is just equal to I minus q transpose xn minus mu. Now, it's important to remember that our Q transpose Q is equal to the identity matrix, but Q transpose is not. So, back to our objective function, we want to minimize over mu the sum n equals 1 to n of this Q transpose times xn minus mu squared. Well, one thing to note is that over here on the side, this will make life easier. I minus Q transpose times I minus Q transpose is equal to I minus Q transpose minus Q transpose plus Q, I'm running out of room, there we go, Q transpose Q QQ transpose is equal to I. So this last term is QQ transpose. So that and that cancel each other, and we get that I minus QQ transpose quantity squared is just equal to I minus QQ transpose. So this is going to be a nice little property, and this will help us out because we can write our norm squared here in terms of the inner product. And so we are just now minimizing over mu the sum equals 1 to n of xn minus mu transpose I minus q transpose xn minus mu. And if we're trying to minimize something like this, we take the gradient. Equal to 0. And this is a quadratic form. So we get that this is the gradient with respect to mu. So we get this negative sign that comes out front. We still have our sum to worry about. I minus q transpose xn minus mu. And that's equal to 0. And it's also, let me just put it over here so I can, it's also equal to minus 2 I minus q transpose, which is now no longer a function of this sum. And as far as that goes, the only thing that's a function of n here is x of n. And we can pull that out of the sum as well. So we want this to be equal to 0. I minus QQ transpose is not. Therefore, we need to have mu is equal to 1 over n times the sum equals 1 to n x of n. So we find that mu is just the average of all the observed vectors. Okay, let's sum up what we know with respect to PCA, and that is first, remove the mean. Where this is the sample mean. Now, if you have something that you know comes from a zero mean process, you can, of course, just skip that step. Then 2, define capital X tilde as the matrix of all the data samples. 3, find our SVD, U sigma V, and set Q hat is equal to UK for whatever your desired value of K is. And our individual projection vectors look like that. And you can think of this theta sub n as the k-dimensional representation of our d-dimensional vectors x. So this is our subspace. And mu, of course, is the offset, which gives us our affine space. Now, the nice thing about this is, if we have later samples, we can project them onto our reduced dimension subspace, spanned by Q. After, of course, subtracting out the mu if that's a necessary step. So we can then, once we've found our transformation, we can apply that to other vectors. Now, one thing that's very useful to know about the PCA is that in statistics, they'll often start the whole problem by viewing it, creating a data matrix, and then finding the eigenvalue decomposition of that data matrix. And you'll see this often in textbooks. Data matrix is often called the S matrix. And then you pick off the k largest eigenvalues and use that to approximate your data. Well, it so turns out that the math, although it's couched in a different framework, this SVD framework to me makes more sense. It turns out that we're doing exactly the same operations. And so using PCA is a good way of taking high dimensional data and reducing it to fewer dimensions. And one of the things that's often done in this process is when you take the SVD, you look at the singular values, and people will often choose, say, enough singular values that 90 or 95% of the energy is contained within those singular values, so those singular values which are small are ignored. And depending on your data, this may actually be most of the dimensions, or it may be very few.